In 1999, id Software released Quake III Arena, a pioneer in 3D gaming. Buried inside its source code was a bizarre math function called the fast inverse square root. It contained a single, baffling line of code, featuring a seemingly random hexadecimal constant and an infamous comment from a very confused developer. Today we're going to break down the most famous hack in computer science. To understand why this code exists, we have to look at 3D graphics. To calculate how light hits a surface, engines use normal vectors, arrows pointing straight out from polygons. By comparing these normal vectors to a light source, the game computes shading and reflections. But there's a catch. For the math to work, these vectors must be normalized. Let's take a standard 2D vector as an example. To normalize it, we first find its length using the Pythagorean theorem. In this case, the length is about 3.61. Then we divide the original vector by this length. This shrinks it down to a length of exactly 1, making it a unit vector. Now it only represents pure direction. Mathematically, dividing by the length means multiplying by 1 over the square root of x. This is the inverse square root. Back in the 90s, processors had a major bottleneck. Basic operations like addition and multiplication were extremely fast, taking just one CPU cycle. But division and square roots? Those were brutally slow, taking up to 30 or 40 cycles. With millions of normal vectors to calculate every single frame, the CPU would become completely overwhelmed. So the programmers faced an impossible challenge. Can we estimate the inverse square root using only fast operations? To solve this, we have to look at how computers store decimal numbers. Numbers like 16.34 are stored in the IEEE 754 floating point format. It uses 32 bits divided into 3 parts: a sign bit, an 8-bit exponent, and a 23-bit mantissa. These bits are plugged into a specific mathematical formula to represent the decimal value. The first step of the hack is to lie to the computer. We take the floating point bits and tell the CPU to treat them as an integer. It's the exact same bits in memory, but now the computer reads it as a massive whole number. Step 2 is where the magic happens. A bitwise right shift. By shifting all the bits to the right by 1 position, we are essentially dividing the integer representation by 2. Because of how floating point numbers are structured, shifting the bits like this halves the exponent, which perfectly approximates taking the square root. But shifting bits messes up the mantissa and introduces a huge error. That's where the magic constant comes in. By subtracting our shifted bits from this specific hexadecimal number, we correct the error and simultaneously flip the value to get the inverse. If we plot the true inverse square root function and overlay the results of our bit shifting magic number, we get a curve that is roughly 97% accurate, with no division and no square roots. 97% is good, but Quake needed better. Enter Newton's method. Newton's method is a calculus trick to find the roots of an equation. We start with our 97% accurate guess from the magic number. We draw a tangent line at that point and find where it intersects the x-axis to get an even better guess. The code does exactly one iteration of this mathematically simplified formula. Notice that it only uses subtraction and multiplication. Still no division. Compared to the true mathematical answer, this single refinement brings the accuracy up to an astonishing 99.8%. Let's compare the performance. A traditional inverse square root took around 30 CPU cycles to compute. The fast inverse square root hack, with bit shifting and 1 Newton iteration, took only about 7 cycles. It was roughly 4 times faster while maintaining near-perfect accuracy. So who actually wrote this masterpiece? Its origins trace back to 1980s supercomputers, tweaked by minds like Cleve Moeller and Greg Walsh before making its way into Quake III. Even John Carmack, the lead programmer of Quake, admitted he didn't write it. Today, this code is obsolete. Modern Intel and AMD processors have specialized hardware instructions built directly into the silicon to do this instantly. But it remains a beautiful reminder. Sometimes, to solve an impossible problem, you have to stop playing by the rules of math and start playing with the machine itself. Thank you for watching Luminous Math. If you want to see more visualizations of the most fascinating mysteries in mathematics, hit subscribe, and I'll see you in the next one.